Just briefly, though, to begin with, a couple of you asked me yesterday near the end of the day when our unit exam is here. We've had one exam so far which covered chapters 1 and 2. This is a monster unit. It covers chapters 3, which is basically rates and related rates, chapter 4, which is basically what we're working on now and what led up to it, and chapter 5, which is graphing. And I've got the unit exam slated for 3 weeks from today. So we're going to spend the next couple of days today, both in the seminar and in the regular class, and also tomorrow in the regular class, finishing up with optimization, looking at some other problems. And then for the next couple of weeks, we'll be doing chapter 5, which is curve sketching, which is basically, at the end of chapter 5, you should be able to be given a function and come up with a very detailed sketch on paper. I know it seems like we're going backwards because we have technology that can graph things, but use calculus to come up with a very detailed, very beautiful graph of the function, much better than you could come up with on a graphing calculator. Because on a graphing calculator, there may be details of a function that you're unaware of, and they may be off the screen somewhere, so you don't know where to look for them. But the calculus tells us where all of these features are. So anyway, unless things change, we're looking at April 26th for the next unit exam. So with not related rates, with max-min, again, you want to come up with an equation that connects the thing you want to maximize or minimize to a single variable, some variable. And that way, maybe to just slow things right down here and get more to the point, if O is the variable to be optimized, so that could be the area of a rectangular enclosure, it could be the volume of an object, it could be the surface area of an object. If O is the variable to be optimized, and O is defined in terms of X. I know I said yesterday to avoid using X as a variable, but maybe I'll amend that. Yesterday, I believe I said avoid using X and Y as variables. And the reason is you might paint yourself into a corner by ending up having Y be the independent variable when you do some algebra. That just can cause confusion because then your Y variable would be on the horizontal axis and you would be finding dO dy, which seems a little strange. Anyway, I'm just using X here. So if you define O to be the variable to be optimized, and if you define O in terms of X, I'm not going to write this, but and only in terms of X, not in terms of some other variable or multiple variables, then dO dx leads you to the critical values of X, which lead you to the answer to the problem. And the problem may be that it's just what is the value of X that makes it happen, in which case that's the answer. It may be what is the optimized value of the variable. What is the maximum area, in which case you use that critical value of X along with your function for O to calculate O. I mean, this is it in a nutshell. What I've got up here is essentially what I'm saying with this stuff. The third point here is just reminding you that if you get multiple critical values of that independent variable, you have to sleuth out which of those variables values, which of those critical variable values leads to the actual answer. And we haven't encountered anything yet where you have to do a first derivative chart to do that. We've just encountered situations where you get a list of critical values and you go, well, it can't be that because that's negative, or it can't be that because that's 0. But sooner or later, and I suspect it's going to happen today or tomorrow, many of you will encounter cases where you will have to do that. So does anybody have any questions, general or specific, to anything you've been working on here? Go ahead, Zebby. Number 5. So I'm going to, I know that I set this up yesterday, but I'm going to run through it from the beginning, just in case somebody's watching this video from the seminar. A square base open top box has a volume of 4,000 centimeters cubed. When you're talking about a box with a square base and an open top, what we are talking about is something that looks like this diagram on the left. Okay? And this is where we introduce the variables. We say, well, we have to call this something, and we need to call the height something. So those are the variables I'm going to have. The only condition is that when you find the volume of the box, the volume has to be 4,000. Okay? So once again, and we went through this yesterday, but I'm going to talk about it again here. We have a constraint that is volume must be 4,000 cubic centimeters. We can turn that into an equation of constraint by taking the formula for the volume, which is length times width times height equals volume, and applying it to that diagram, so it's going to be S times H. Right? So this 4,000 is S squared H, and this is the equation of constraint. Our optimization angle to this question. So I guess what I'm getting at by saying optimization angle is very often in max-min problems, you have two mathematical ideas or equations or relations or whatever you would like to call them. And one of them is a constraint, where it connects all of the variables to some value that they have to collectively have. The other one is an optimization angle. And the optimization is that we want the area to be as small as possible. And I actually want to stop here and just tell everybody something. I know you're asking about this question, but I'm going to use it as a springboard to discuss something in more broad terms. Sometimes we'll do a question like this and we'll get an answer, and then a student will say, how would you solve it if it said maximizes? That's a great question. But the answer that I would provide is, it wouldn't say maximizes because there's no maximum area. If you were to look at the graph of area as a function of one of these variables, it will take off to infinity. And we can kind of see that because I could make the base of this box so exceedingly tiny, like 1/millionth of a centimeter by 1/millionth of a centimeter, and that would make the height extremely tall, which would explode the area. So you will never be asked to find a minimization standard if it is actually a maximization standard, or vice versa. Okay? So you can take it to the bank that if there's only one critical number, it's going to minimize the area. That's my point. So the constraint leads us to this equation on the right. The optimization angle leads us to this equation. I'm not using the letter O, I'm using A. So A is a variable that has to be in the equation because you want to find dAd something. And not always, but if your function defining the thing you want to optimize defines it in terms of more than one other type of variable, that's where the equation of constraint comes in. So this is where we would have to take this and eliminate a variable here. And we talked yesterday in class about the fact that I guess you could rearrange the equation of constraint for S and do two substitutions. there's two problems with doing that in my mind. One, you're going to have more work to do because you have to put s in two places. And two, when you rearrange that equation for s, you're going to get square roots. And who needs that if you don't have to have it? So I rearrange this equation for h, and I get 4,000. And it's over s squared, so I'm just going to put it as s to the negative 2, and it seems like you're okay with that. So I'm going to put that in for h, and I get a equals s squared plus 4s times 4,000 s to the negative 2. And I understand, Zebby, that I did all this yesterday, so your question probably lies in stuff near the end, and we'll get there. So just be patient, please. I'm going to simplify this. Ultimately, my goal here now is to find dA ds so I can find the critical values of s so that I can get the answer to the problem. But before I find dA ds, it's a smart thing to simplify that. So when I do so, I get a equals s squared plus 4 times 4,000 is 16,000. S to the 1 times s to the negative 2 is s to the negative 1. Now here's an interesting thing. And it's, again, I kind of like these seminars for very few reasons, but this is one of them. A thought occurred to me, and if I were in class right now, I'd probably go, don't worry about that, Paul. Don't touch that, because we got to move on. We have a bit of time here. Very often what happens, good morning. Very often what happens is you go through all this work, and it is a lot of work so far. And then what I see students do is they start factoring this. They set it equal to 0 to find the critical values of s, but they've forgotten a key component to this process, which is you have to differentiate this. Right? Some of you might have already been thinking of doing that, and others would be probably thinking, why would you do that? You have to differentiate it. No matter what level you're at, sooner or later, you end up getting caught into that trap. You end up getting sucked into that trap where you want to find critical values here. We're not finding critical values of this. We're finding critical values of the derivative. So we have to differentiate dA ds and get 2s minus 16,000 s to the negative 2. So Zebby, are you fine up to that point, including the derivative? Okay. Now what we want to do is work on the critical values of s. And again, the cleanest way, and I've kind of modeled this mathematical behavior from day one, the cleanest way is always to factor things. That's how you solve equations at this level. So I can factor a 2 out, and I can factor s to the negative 2 out. We always want to factor the negative exponent, or maybe in general what I will say is you always want to factor out the lowest exponent on the variable. Negative 2 is lower than 1. What will we have left? I will have s cubed minus 8,000. So Zebby, just roll that around in your head for a second and see if that makes sense, how I got s cubed. Okay, so there's two ways to do it. Well, yeah, there are two ways to do it. So I'm going to go back and just review some fundamental factoring here. If I had (2x squared minus 30), and I said factor that. You factor the 2 out, and you're left with x squared minus 15, and I think that's pretty obvious, right? And I'm going to go out on a limb here, Zebby, and guess that you know it's 15 because your brain says 15 times 2 gives you 30. You know that. Did you by chance figure out that it's 15 by going 30 divided by 2 in your head? You did, okay. Well, maybe that's even better to my point. I don't necessarily do division when I factor. I don't know why. I just ask myself, what would I multiply by the thing I factored out to get what I started off with? But when you factor, you divide. So what's going on here? What's going on here is if I'm going to factor out 2s to the negative 2, then I have to take the 2s to the negative 2, and what I'm going to have inside will be 2s to the 1 divided by 2s to the negative 2 minus 16,000 s to the negative 2 divided by 2s to the negative 2. When you're factoring, you're dividing. And it's unfortunate that I erased that example of 2x squared minus 30, but the division that occurs usually in factoring is something that just your brain grabs a hold of the wheel and drives for you. It's autopilot. It just happens. You don't have to consciously think about it. But how we're getting s cubed is that if I divide 2s to the 1, which is what I started with, by the thing I factored out, I'm going to have the 2's canceling, and I'll have s to the 1 over s to the negative 2, which is s cubed. Is that okay? That is not how I would do it, and I'm just going to explain how I do it. And this goes back to me knowing that this number is 15, because I don't say what is 30 divided by 2. I really don't. I say what multiplied by 2 gives you 30. And I'm not going to do division anywhere. I'm just going to go, oh, well, 15 times 2 gives me 30. So over here, when I say, we don't have a problem with the 2, right? When I say, what's the exponent on this, I'm saying that these two things multiplied together have to give me s to the 1. It's like me saying the missing number over here multiplied by 2 has to give me 30. So I ask myself, what exponent would I put on s so that when I multiplied s to that exponent by s to the negative 2, I would get s to the 1? Well, I know that I add exponents when I multiply common bases. So I need to add 3 to negative 2 to get 1. So are we okay to this now? Okay. What this means, I'll just write it over here so we can see the whole thing on one screen, is dA ds is 2 times s cubed minus 8,000 over s squared. So we have critical values of s that are determined by what numbers make the derivative equal to 0. And the answer is the cube root of 8,000. And are you okay with that? So, I mean, I suppose we could, again, don't factor it. I think factoring it is a waste of time as a difference of cubes. But you could write s cubed equals 8,000, add 8,000 to both sides and take the cube root. But it's 20. The cube root of 8,000 is 20. The other critical value of s is the other condition for critical values of s is, are there any values of s that make the derivative undefined? And the answer is yes. When s is 0, the denominator is 0, which means it's undefined. By the way, we haven't encountered any yet. You might kind of be under the misapprehension that the critical value making the derivative undefined is never a solution. Sometimes it is. Okay, sometimes it will be. But in this case, if s is an actual dimension of the box, and these are the only two critical values of s, then we cannot use 0. Really, what we're saying in this function here is that the domain is s is greater than 0. Right? You can't have a 0s, you can't have a negative s, because s is a dimension of a box that exists. So now we know s is 20. What the dimensions are that would minimize the box would be, if s is 20, 20 by 20, by whatever the height is, and we can determine the height by going up to our equation of constraint. The equation of constraint, I'm just going to write it as 4,000 equals s squared h. So if we put S in and solve for H, I believe we get 10. By 20 by 10, which, that's interesting. I didn't do this intentionally, but I believe that was the dimensions I threw on one of the boxes I showed here. And I only did that because I was looking for numbers that multiplied to give 4,000 so that it didn't have square roots or some weird thing. So I happened to guess. Okay. Are you fine with that now, Zebby? Okay. We only have a few minutes left, but that's okay. Any other questions? Go ahead. Okay, let's take a look at number 6. I suspect that I can get started on number 6, and then if we need to, we can discuss the rest of the solution in class this afternoon. This is a case where we are taking a piece of paper, we're cutting out corners, and we're folding up So we're taking this sheet of paper that you're looking at here before the corners are cut out. We're cutting out square corners, and then we're folding this up to get a box, something with volume. The only difference, one of the differences between what I'm showing you here with this piece of paper and what we're looking at on the screen is this started off as a rectangle and this is starting off as a square. Okay. But when we fold this up, if we call this distance here x and this distance x, and the entire distance is 3 meters, then when we remove that x and fold up the flaps, the height of this is going to be x. And you can see that here with this sheet of paper, that if the distance between my fingertips is x, when I fold that up, that's the height of the box. Okay. The base of the box, the thing that I'm just going to pepper with this red, the base of the box is this. So when I take a look at this box, and I'm not a big fan of this particular diagram, but this would be 3 minus 2x. Because it starts off as being a length of 3. The flaps each have x, which the corners get removed, and the flaps, which are each x, get folded up, so the x is removed from both sides of the 3. And this dimension as well will be 3 minus 2x. I maybe got a little bit ahead of myself because I'm so familiar with this particular problem, but if we start with what we're trying to do, what we're trying to do is optimize V. And what that means, it says what is the largest volume. What that means is we need a formula for V. So we start off with this idea that volume equals length times width times height. And then we take a step in the direction of saying, well, but you know what? We need a variable. We can't just use length and width and height. So let's introduce this variable of x. Then I can define my length, width, and height in terms of x. And now I have my formula, which is volume equals 3 minus 2x multiplied by 3 minus 2x multiplied by x. And the bell's going to ring here, and I want to finish my thought so that I don't get interrupted. You need to find dv dx. You need to simplify this by multiplying these two binomials out with FOIL, multiplying the result by x to get a degree 3 polynomial, which means dv dx is going to be a degree 2 polynomial. When you differentiate a degree 3 polynomial, you're going to get a degree 2 polynomial. To find the critical values here, you would set it equal to 0. And I'm guessing that it's not going to be factorable. So we'll finish that this afternoon. Did I write something down wrong there? No? Okay.